Okay, and we're live. So hello everyone, and welcome to today's Exploring by the Seat of Your Pants Hangout. My name is Melissa, and I am going to be your host for the day. So joining us today, we have Daniel Devost. He is the Director of Science Operations at the Canada-France-Hawaii Telescope, and he's going to explain to us a bit about how the telescope works and the mysteries of our universe that the astronomers are trying to unravel. The Canada-France-Hawaii Observatory, as CFH for short, hosts a world-class 3.6 meter optical infrared telescope. So the observatory is located atop the summit of Maunakea, a 4,200 meter dormant volcano located on the island of Hawaii. So with that, I would like to hand it over to Mr. Devost.
Hello, thank you, Melissa. Hi, everyone. So thanks for coming and joining this wonderful hangout. So my name is Daniel Devost. I'm the Director of Science here at the Canada-France-Hawaii Telescope, and I'm in the remote observing room right now, which is where the observations happened last night. So until 6 or 7 this morning, there was someone here in this room conducting observations. You can see behind me all of the screens and gizmos that we use. So I'm going to start my presentation and share my screen. So if you give me 1 second. Okay, so you can see it, Melissa?
I can, it looks great.
Okay, so today I'm going to talk to you about our telescope, the Canada-France-Hawaii Telescope, and how we do science with professional telescopes on Maunakea. So, like Melissa said, we're located right in the middle of the Pacific on the islands of Hawaii. So we're located on the big island. So it's an archipelago of several islands. So we're on the biggest one, the big island. And we're on the summit of Maunakea, which is close to 4,000 meters high. So here's the altitude, and the fact that we are in the middle of the ocean makes Maunakea one of the best sites in the world for astronomy. And if you have, I can explain that in the question period for you, why that is. So here's the summit of Maunakea, and the CFHT is in the red circle. So there's 13 telescopes up there, and they're all in different ways gathering data for astronomers all around the world. So for us, CFHT, so that's a picture of our dome. So 5 partners can ask for time at CFHT. So you have them down here in the red box. So France, scientists from France ask for time, scientists from Canada, from the University of Hawaii, and we have also scientists that ask for time for China, and scientists that ask for time from Taiwan. So every year, astronomers from these countries and institutions ask for time on CFHT, and we receive all these proposals for time on the telescope, and only the best programs get time on the telescope. We're oversubscribed by about a factor of 2, which means that there's about twice as many time proposals than we can give in the whole year, because there's only 365 nights in a year. So now let's go inside the observatory. So like Melissa was saying, CFHT is a 3.6 meter telescope. So 3.6 meters, the diameter of the primary mirror. So this is how we estimate the size of telescopes. It's bigger, it's better. We always try to have bigger mirrors. So CFHT was built some close to 40 years ago. And at the time, 3.6 meter was pretty big. Now today there's bigger telescopes, of course. And CFHT still makes its mark on the science arena. So you can see here, just to give you an idea of scale, the building is 5 story tall, the building itself. And you can see here inside the dome, 3 members of our day crew discussing something. So it's a big telescope, it's a big space. So first thing I'm going to talk to you about is instruments. So one very important thing that telescopes have are instruments, and instruments are really the tools of astronomers. They allow us to study the universe in different ways. Each instrument is unique, and each have a different way to look at the night sky. So I'll talk to you about our instruments, but first, let's do a little bit of history. So this is Galileo Galilei observing the sky in the late 1500, early 1600. So he had two instruments, right? At that time, there was no real electronics, there was no electricity. So only his eye to observe the heaven and his hand to record what he was saying were used as instruments, if I can say that. So in 1609, using these two instruments, he discovered the four moons of Jupiter, Io, Europa, Ganymede, and Callisto. And night after night, he drew their positions and discovered that they were orbiting Jupiter. So you have here the drawings that he made. So he was looking into his telescope, recording, drawing, and doing that night after night. So today, of course, we can still do it like that, but even in professional astronomy, we don't do it like that anymore. But amateur astronomers, even them, can use electronic recording equipment. So amateur astronomers use telescopes and commercial cameras to record their data and take wonderful pictures of the sky. So in this example that you have here, this little camera that's at the focal plane of that telescope is called an instrument. So when I refer to instrument, this is what I mean. Some kind of camera that records the data. So just so you guys don't get confused when I call instruments. So at CFHT, we have 4 operating instruments. So astronomers love to give name to their instruments, and usually acronyms, so I won't explain them, but our 4 instruments are named MegaCam, WearCam, Espadon, and SITELLE. So first, MegaCam, it's a 6-meter tall camera, and it has 377 megapixels that record optical light. So it means that it records light that you can see with your eyes. So the biggest advantage of this camera is that it has a huge field of view. It records, it lays those 377 million pixels on an area equal to 4 times the size of the moon. So in astronomy, that's a big size. It's big pictures. So it thus records a large amount of data within one single picture. And this allows us to study large volumes of our universe. And I'll talk about that a little later, the science we do with that. Our other camera is called WearCam, and it's also a large camera located at the prime focus of the telescope. So MegaCam and WearCam, they're cameras that go on the top of the telescope. And here in the little red circle, you see that where WearCam is, and MegaCam goes at the same place. So it's literally the camera that's up in the air, 100 feet, I think, maybe in the air or something like that. So you can see here WearCam. What it does, it records infrared light, and this light is invisible to our eyes. So MegaCam light is visible to your eyes, at least some of it. WearCam light is invisible. It's infrared light. So what is infrared light? So let me give you a couple of examples that we do with an infrared camera. So it records temperature and can see through material that is opaque to the human eye. That means that we can't see through it. So here's an example of temperature recording. So you have 2 glasses here, one that contains hot water and cold water. And if you take a picture with an optical camera, which is a regular camera that you use every day, you can't see any difference other than the color, but you cannot tell which one's hotter than the other. However, if you use an infrared camera, you can see that the red glass has hot water in it, and the blue glass has cold water in it. So in astronomy, we do the same thing. We use these infrared cameras to measure temperature and all sorts of other things. So here you can see an example of the see-through capabilities of infrared cameras. So you can see through a trash bag here, so which you can't with an optical camera. And you can also record the temperature, the skin temperature of the person that's holding the bag. So two birds in one stone. So how do we do science with cameras? So very quickly. So what we have here is a cartoon representation of a camera. It's not a real camera, but it's just for explanation purpose. It tells you how we record the light with them. So on the left, you have the detector, which is a real detector. That's MegaCam's detector. And on the right, you have a filter, and that particular filter is red. And on the right side of that filter, you have light coming from the telescope, which I image here as beams of light. And they go through the filter, then only the red comes through, and this gets recorded on the left as star images. So you have several stars, you record them all at a time. You don't lose any star, you have several stars in your field. So then you go ahead and change your filter to a green filter, and you do the same thing. And then you move on to a blue filter, and then what you get in the end are 3 images, each of them in one color. And you can plot the intensity of each color, in a graph. So that tells you if the object is a blue object or a red object. So here in this case, we have a red object because the red light is way more intense than the blue light. And you can be fancy and add infrared colors to that. So you could go ahead and do the same thing with WIRCam and then go even further and further and further in the red. And then you have a good idea of whatever source you're looking at looks like in all these colors. So the technical term for this is a spectral energy distribution. So that's a big, huge name the astronomer gives. But basically what you do is you record the intensity of different colors. And then you can go ahead and get really fancy and compare all these points, data points, to your theory. So your theory comes from whatever you think is happening in there. If you think it's a star, if you think it's any type of object, and then this black line is what you think that this is, and you compare your theory with your data. And then here you can see, if you look at the points that are further to the right, they don't fit the data really well, right? They're above, they don't fit the model, I'm sorry, really well. They're above it a little. So something is wrong with your model. So when you use imagers in astronomy, that's pretty much what you do. You do this all the time, and you refine your theory, you refine your models, and you try to basically win the Nobel Prize while you're at it. So another instrument that we have on CFHT is called Espadon, and that's a spectrograph and a polarimeter. So I won't touch the polarimetry side of it. I'll just talk to you about the spectrograph side of it. So this spectrograph, this instrument, comes in 2 parts. There's one part on the left that's attached to the telescope, and the blue link there represents a 30 meter of optical fiber that link the telescope to the spectrograph. And the spectrograph is on the right, and that's where light is recorded. And we have a camera in there. So basically the principle of a spectrograph is simple. Again, we use that tool, that cartoon tool. So that's the camera that, like we talked about earlier. So when you use a spectrograph, what you do, you replace, and again, it's an oversimplification, you replace your filter by a prism or any other optical element that splits light into its colors, right? I'm sure most of you know that when you send light to a prism, what do you get? You get colors, basically. It splits, the prism splits the light into its different color components. So light, however, is collected only from one star at a time with Espadon. There are some spectrographs that can collect more than one star at a time, but it gets very difficult to do. So you're limited in the number of stars that you can observe with a spectrograph, but in exchange for that, you get all the colors. So here you can see it goes from the red to the blue, and basically what we do, we record the picture of the rainbow of a star in a spectrograph. So we use cameras again, but in a different way. And then what we get with that, in the end, you get several colors. And in these colors, you can notice the presence of dark bands here. These are due to elements that are present in the star. So let's zoom in a little in that spectrograph and see this. Here, this part of the spectrum shows magnesium, iron, sodium, and hydrogen. And I've highlighted the sodium line, so it looks like a depression in the intensity of that particular color. And in the color spectrum that's on the top, you can see a darker band. So basically, spectrographs are extremely useful in astronomy to figure out what a star is made of, what components are in the star. So last instrument is called SITELLE. So it's the latest instrument at CFHT, and it is an imaging spectrograph. So that means that you can take a regular image, basically a normal image, just like you do with megacam, but you get a spectrum for each object in the image. So remember, I was telling you earlier that when you use a spectrograph like espadon, for technical reasons that I won't explain here, you're limited to one star. But if you use megacam, you can record a lot of stars, but you can only record one color at a time. With a spectrograph, you can record a limited number of stars, espadon's down to one, but you get all the colors. You get a ton of colors. So SITELLE does both. And that's really the uniqueness of this instrument, is that it enables you to record all the stars in the field and get the colors of each and every one of these stars. So it's a very complicated instrument, honestly, and it came from Canada, actually. It came from Quebec City. It was built by Laval University and a company called ABB in Quebec City. And it's been on the telescope here for about a year. So this is an example of what can be done with SITELLE. So this is a velocity field of a galaxy. So what does that mean? Is that how the objects that you see in that image move with respect to us. So the blue ones are the ones that are moving toward us. And the red ones are the ones that are objects that are moving away from us. And the green and yellow ones are somewhere in between. So this is a very powerful technique, and it allows you to understand how galaxies rotate and how things go around each other. So something that's really hard to do, even if you try it with espadon or with any other of our instruments. But with SITELLE, you can do it. So that was just one example. So this is it. These are the four instruments that we're using at CFHT. We operate them on a regular basis, one at a time on the telescope. Right now, it's megacam that's on the telescope. And I'll show you in the next few slides some of the science that we do at CFHT that were done using CFHT cameras. So I'll talk to you about dark matter, dark energy, and a new instrument to search for and characterize planets similar to our Earth's around red stars. So stars that are redder than the sun. So the sun is kind of a yellowish star. So stars have colors. Like I showed you earlier, if you take different pictures in red, green, and blue, you'll see that a red star has more intensity in the red. A blue star has more intensity in the blue. So this new instrument that will come to CFHT, it's now being built in France and in Canada. It will try to find and characterize planets similar to our Earth's around red stars. So first, dark matter and dark energy. So I'll talk to you a little bit about the dark side of our universe. So here's what we know of the universe. And honestly, it's not that much. As you can see here on this pie chart, 75% of the universe is something we call dark energy. We call it dark energy because we don't know what it is. And same thing for dark matter. 21% of the universe is dark matter. And we do not know what dark matter is. One thing we know is the 4% of normal matter. So when you talk about normal matter, it's everything you find around us. Iron, oxygen in the air, nitrogen, the air, the atoms, all that stuff, and more. I mean, neutrinos, and if you include all these exotic particles, there's about 4% of it in the whole universe. So this is called normal matter. So this is all we know about the universe. So the dark universe is really a mystery, and we're working hard here at CFHT and many other astronomers to try to figure out what this is. So here's how we detect dark matter. So this is a Hubble picture. So mass distorts light and produces arcs and filaments visible in this image. So you see arcs and filaments that seem to be centered around this bright spot in the middle. And this is basically called gravitational lensing. So here's the effect. So basically what you have a central mass that acts as a lens, and it's like an optical lens. When you look through a lens, you see things behind it that are distorted. So this mass at the center distorts the light coming from a galaxy behind it, a background galaxy. And what you see when you look at it from Earth is something like that, distortions that are all over the place. So what you can do is measure these distortions and figure out what the matter that distorts all this light is. And the amount of dark matter here shown in blue can be derived using these distortions of galaxies in megacam images. So in order to be able to do that, you need to take huge pictures of the sky, and megacam is perfect for that. Here, the distortions are hard to see. It's not as evident as the other image. So this is a megacam image. It's more subtle, but it's a technique that involves measuring that. So this blue part, we don't really see it. It's been added to the image. What you do see is those yellow galaxies that are in the field. But this blue part is what we derive using the distortions of all the galaxies that we see around it. So this is an indirect measurement of dark matter. So we think that there's dark matter there, this blue area. Now let's go on to dark energy. Dark energy is more complicated, so I'll just skim to the essential things. So it's measured by using something we call standard candle and standard ruler. So I'll just talk about the standard candle. So if you have a candle and you move it farther away, it becomes fainter and fainter and fainter. And if you know how bright your candle is, you can know its distance by measuring its brightness. So what we do in order to measure dark energy is that we measure the brightness of the standard candle and thus the distance, and in two different ways. We measure the distance using the brightness and another way that I won't explain. And you basically compare these two measurements, and you end up with a difference that actually tells us that the universe is accelerating. There's a force pushing on the universe that makes it accelerate. It doesn't only expand at a constant speed, it accelerates, just like when you push the gas and when you're in a car and you push on the brakes, that's a deceleration. So the universe, there is acceleration in the universe. And this is what we call dark energy, and we have absolutely no idea what this energy comes from. So the standard candle we use is supernovae. So astronomers using CFHT were able to detect hundreds of supernovae and use them as standard candle to measure the expansion of the universe and characterize dark energy. So the way you do it is that you take pictures of the same area. So you can see here 3 weeks before supernovae discovery. So you go back to the same field, and if something has changed, then you look at it and whoops, there it is, supernova. You make the difference between the two images. Everything should be the same except for the supernova. So that's how you detect them. So we had a program several years ago that was just tailored to do that. Just looking at patches of the sky over and over again and basically discovering supernova. So this is discovered hundreds of them. So now let's move on to exoplanets. So basically what we're looking for there is life in the universe. And this is a field that's in constant expansion. You can see here on this graph that shows the number of exoplanets discovered as a function of time. And more, right now we know that there's more than 1,000 planets around other stars. So there's more than 1,000 stars that have planets around them, I should say. It says it better. And these have been confirmed only over the last few years. And this shows, this graph shows the number of planets discovered and the method used to discover them. So there's several methods to discover planets. I won't go through all of them. There's radial velocity, pulsar, primary transit, microlensing, imaging, astrometry. And basically the primary transit is the one that's used the most now. The new instrument we're going to have is going to use radial velocity. So I won't explain the method in detail, but it's a method that's really difficult. But we think we can do it with our new instrument that's going to be called Spirou. So it may ring a bell. It's an instrument that's similar to Espadon, and it's a new instrument that will come soon to CFHT to use the radial velocity method to discover planets around stars smaller and redder than the sun. So it's really a particular type of stars that we're targeting with this instrument. So it will work in the infrared, so like WRCAM, it will work in the infrared, not in the optical, and it will observe the spectra and also measure the magnetic field of these stars. And that will help us find and characterize planets around these stars. So I think I will stop here. I've done over 20 minutes a little. I'm sorry about that. Science at CFHT goes from stars and planets to our neighborhood to very distant galaxies using 4 state-of-the-art instruments. CFHT helps us understand basic questions about our universe and planets around other stars. So I will stop here.
Excellent. Thank you so much, Daniel. So we have a ton of great classrooms who I know are going to want to ask some questions. So I'm just going to go in order on my list here. So first we have Miss Lou's class from San Jose, California. I'm going to unmute your microphone and you can go ahead.
Oh, Daniel, can I ask your question? Clicker. We were going to ask you, we're in 5th grade at Blackford School, and we're going to ask you about dark matter. Like, if you could explain dark matter again.
Excuse me, can you speak up a little? I could barely hear you, I'm sorry.
We're Blackford School Elementary, and we're in 5th grade, and we're going to ask you if we could, if you can explain dark matter.
Explain dark matter, okay. So basically, like I showed in my presentation, we can only see it in indirect ways. So what I was saying in the presentations with that is distorts light. So we don't know what it's made of, but we know it's there. And there are several theories to try to understand what it is made of. We know that there's about 10 times more of it than there's regular matter. So wherever you look where there's galaxies and you can count them one by one, you can assume that there's about 10 times more dark matter in this area. So there's been several theories to try to explain what this is. None of them right now is satisfactory or implies something that we can easily understand. So the jury is still out there, but there's several hypotheses from exotic particles, relativistic photons, and all of these types of things.
So the answer is that we don't know what dark matter is.
Right. It's a long way to say.
Awesome. Yeah. So what scientists are doing is they're trying to come up with some theories. So maybe you guys will be part of the team that discovers what dark matter is.
That's right.
Awesome. Thank you. Great question. Okay. So next on my list is Ms. Barajas's class in Oxnard, California. If you guys want to ask a question, go ahead. Do you guys have a question?
I don't have a question.
No? Okay. Keep thinking and we'll come back to you in a bit. Okay, so Madame Bourque's class in Calgary, Alberta. I'm going to unmute your microphone. Go ahead.
David, tu peux le demander en français? Tourne-toi.
Oui, vous pouvez parler en français, bien sûr.
Est-ce que vous avez une map de toutes les planètes qui sont découvertes? Approche-toi, parle plus fort. Penche-toi. Penche-toi.
Oui, j'ai pas compris.
Parle plus lentement, David.
Est-ce que vous savez une map de toutes les planètes que vous avez découvertes?
Est-ce qu'on sait...
Est-ce que vous avez une carte de toutes les planètes que vous avez découvertes?
Je n'ai pas de carte avec moi, mais oui, il y a une carte. On sait où les planètes sont situées parce qu'on sait où les étoiles sont localisées.
Okay.
Donc, on trouve une planète autour d'une étoile, on sait où cette étoile est, on la suit, et puis on a une carte, si vous voulez. Vous pouvez avoir une carte du ciel avec la location de toutes les étoiles. Une qui a fait les nouvelles beaucoup, c'est la planète autour de Proxima Centauri, qui est une étoile dans l'hémisphère sud, mais qui est visible, je pense, l'été de l'hémisphère nord, d'ici à Hawaï. Et cette étoile est la plus proche du Soleil. Donc, il y a beaucoup de chances que ce soit la première étoile qu'on visite si jamais on réussit à voyager par des étoiles. Ça prendrait 4 années à se rendre à cette étoile à la vitesse de la lumière. Donc, c'est très loin. Ça prendra environ 180 000 ans à se rendre là en utilisant les fusées les plus fortes, les plus powerful qu'on a sur Terre.
Donc, comment elle s'appelle cette étoile-là?
Proxima Centauri.
Proxima Centauri. Merci beaucoup.
Et dans la constellation du Centaure, et puis Proxima, ça veut dire que c'est la plus proche.
OK.
Excellent.
Merci.
Thank you. So that question for our English-speaking classes, that question was asking about maps of the stars. Do we have a map of the stars? The answer was yes. And then we were talking about where the closest star is, and that is called Proxima Centauri. And that would take 4 years at the speed of light to get there. Cool, huh? Awesome. Thank you very much, Madame Bork's class. Okay, our next class is Mr. Richards in Amherst View, Ontario. Go ahead and ask your question.
You guys come up right on the show. Yeah, go ahead. Nice loud.
Where does the universe end?
Oh, where does the universe end? That's a really good question. And so right now, the model that we have, the best model that we have of the universe, remember during the talk, I was telling you, you compare your theory, your model, you had this line on this graph with all the points. When we do that with the size of the universe, the best model that we have gives us something like 13.8 billion years. So that's the age that we get, and that's also a distance. So you can convert that into a distance. And that's what we think is the edge of the universe. But this is, from my point of view, this is where our understanding of physics ends. And maybe if we develop new physics, we'll be able to understand further away from that. But right now, our understanding of physics and astrophysics tells us that it's at this 13.8 billion years.
Excellent. Thank you.
Great question. Okay, so we're going to keep going through. We have our students joining us from Fort Langley, British Columbia. Do you guys have any questions?
My son would like to know if wormholes exist within dark matter or dark energy, or if that's unrelated.
Okay, wormholes are, they may or may not be, it depends what dark matter is. So one of the things that is explored as being dark matter is black holes. So black holes is in itself dark matter in the fact that we cannot see them. They're attracting all the light toward them. Now, are black holes making dark matter? There's still a question for debate. So people don't really know. It's one candidate, but we don't know. Now, wormholes come from the fact that you have, it's a connection between two black holes, basically. So it's, to answer your question, it might be related to dark matter, but it's really black holes that are responsible for that. And that was a theory that was put forward by Stephen Hawking several years ago. Right now, it's they're not as popular among scientists as they used to be. There's some problem in this theory that were pointed out, and it's not as popular as it was. Scientists don't believe in them as much as they used to.
All right. Thank you.
Awesome question. Thanks, guys. Awesome. So I know we're trying to take a picture of a black hole using a big collaboration, a big team of physicists who are working together. They're all going to point their telescopes at the same area of the sky and take our first picture of a black hole. Can you tell us more about that?
That was supposed to happen last year, and it didn't. And I wonder what happened. So the telescope is called the Event Horizon Telescope. So it's made of several telescopes all around the Earth. And basically, you can use a technique that's called interferometry to combine all these telescopes together and make it like it's a telescope. It's one telescope that's the size of the Earth. So with a telescope the size of the Earth, you can take a very, very, very fine picture of the center of the galaxy, fine enough so that you can have a picture of the surroundings of the black hole and the black hole itself. Of course, the black hole is going to be black, but what they're interested in is the surrounding, what we call the event horizon, where light starts to disappear. That was supposed to happen last year, and I've been looking to see what happened. No, I'm sorry, that was supposed to happen in April this year.
This year, yeah.
I've looked around, I haven't seen anything yet.
They're still working, so hopefully we get that picture soon.
Yeah, they had a 1 week run to do that, and they might have run into problems. It's a complicated telescope. It's very hard to achieve.
Yeah.
I wouldn't be surprised into big problems.
For sure, yeah, but that would be really cool. It'd be the first time we ever took a picture of a black hole, so you'd actually get to see what it looks like.
That's right.
See what's around it. Okay, yeah, I'll make sure to write in the chat the name of that Event Horizon Telescope. Okay, so we're going to go back to Miss Lou's class for some more questions. Miss Lou, do you have a question?
Yeah, why do we have so many screens in the room?
Why do we have what? Oh, so many screens in the back. Oh, very good question. So, yes, so thanks for giving me the occasion to speak about that, actually. So this is what we call our remote observing room. So here, you have all these screens here that are basically used by the observer at night to move the telescope, point it to a certain object, and all of these things. And there's these screens over here where we have weather information. So one thing that's very important is that the observer knows if there's bad weather coming, because that could break the telescope. Basically, if rain or humidity falls on the telescope itself, it can break the optics, because these instruments that we're using, they're very, very sensitive, and they have to be kept dry. So all these screens, it's either running the telescope or looking at the weather and seeing what's coming. And weather, I don't mean only rain, it's measuring the turbulence of the atmosphere, it's wind, rain, of course, humidity, and all of these things. We have a weather station at the summit, and there's several weather sensors also located at the all over the summit to help us track weather. So yeah, that's what we use for.
Great question. Okay.
So somebody typed something, I didn't see what it was. Do I need to answer that, or?
Oh, that was a chat just asking for the name of the Event Horizon Telescope.
Oh, okay.
Awesome. So I sent that. So we have that information in the chat if you're interested. Okay, Miss Barahas's class from Ocean View. Would you guys like to ask a question?
You said regular matter was everything that we could see. Can you give like some examples?
So dark matter is something we can't see. Can you say what you said after that?
Regular matter is something we could see. Can you give like some examples?
Regular matter, yeah. Regular matter, you can see it. It's stars, basically. Stars are made of regular matter, and galaxies that you see, they're all made of regular matter. So you can see it with your eye. If you look at with different types of cameras, you can see different types of matter. And there's X-ray that will make you see also a lot of matter that you can't see with your eye. But yeah, regular matter is really what you see in the sky. So at the beginning, when they discovered dark matter, they were literally counting the number of galaxies that they would see in the field and estimate their mass. And they figured out using some techniques that there wasn't enough mass. There wasn't enough visible matter in this picture, in this field of view, to account for the total mass that was there. There was something there. That was the first discovery, really, of dark matter. And they were looking at how galaxies move away from each other. The velocity dispersion, we call it. And the velocity dispersion wasn't matching the mass that you would have if you count each and every one of the galaxies, which is the regular matter. Today we have much more sophisticated techniques to do that, but it's still the same. There's mass that's missing that we can't see. Did that answer your question?
Yeah, thank you. Why does Jupiter have so many?
Awesome. Okay, thanks, guys. So, Madame Bork's class, do you have another question for us? I'm unmuting your microphone.
How much is there constellations in our galaxy?
So the constellations, I think there's, I'm not really good at that. I think there's 83 or 84 constellations. So there's some of them that are on the path of the sun. So we call them the zodiac. They're the zodiac constellations. And their constellations are an illusion. They don't really exist. So they're a chance alignment of stars in the sky. So when you look at, let's say, something like Orion, that looks like a big, huge giant, if you were able to travel through the stars and go at a different point in our galaxy, then you wouldn't see Orion anymore. You would still see these stars, but they would be in a different pattern. So constellations are really, they're illusions. They're call them chance alignment that invoke a familiar pattern. So that's why different cultures have different constellations. So Orion seems to be on all of them, but the Hawaiians here have a very different view of the constellations that we have. They were using the stars for navigation. It's all centered on navigation. And it's very different from what we know, the Big Dipper and all of these things. So cultures see the sky and constellations differently. So constellations, they're a fragment of our imagination, our collective imagination. They don't really exist. It's not something real.
Yeah. So that's usually we have a lot of great cultural stories and things like that that come out of looking at the sky, and that's where constellations come from. So that's a great question, ladies. Thank you very much.
Thank you.
Okay. What about Mr. Richards' class? Do you guys have a question?
Actually, we're just going to say thank you because we have to get going.
Awesome. Okay. Well, thanks for joining us today.
Thank you.
Bye, guys. Okay. All right. And what about our students in Fort Langley? Do you guys have another question?
Yeah. My daughter wants to know, what is your favorite part of the job there?
My favorite, there's several, I have to admit. I love my job here. I think my favorite part is when there's a big discovery that's made and we had a part in it. We had something to do with it. We contributed images or a spectrum, and you know, these when these are discoveries that really grab the public's attention and make it all over the news, and and when we have a participation in it, that's really, as a scientist, that really makes me feel good about my job. I gotta say, I feel very privileged to work in a research center like CFHT in astronomy. It's very rewarding. We work with high tech, even though we're a 40-year-old telescope. Working with high tech is something I really like also. But the biggest thing, I think, is when there's a big discovery that comes up, and CFHT is part of it.
Okay, thank you.
That's a great question. Awesome. Thank you guys so much. So we are right at our 45-minute mark. So we will say a big thank you to Daniel Devost for joining us from the Canada, France, Hawaii telescope. And I want to say a big thank you to our classes as well. If you guys would like to say goodbye. Okay, thank you guys so much. I hope you have an excellent afternoon or rest of your morning for some of our classes. And thank you again, Daniel.
All right, sure. You're welcome, Melissa. Bye.
Have a great day.
Thanks.